In this segment of the course, we're going to be talking about using formal logic as a way of representing knowledge and performing inference in artificial intelligence. So I think this is a very seductive idea. We tend to think of logical inference as the purest form of intelligence. So there's a sense that we think best when we think logically, and when we make errors in our thinking, we're making logical errors. And logic has some really nice properties as a formalism for knowledge representation. So one nice thing about logic is that it's very flexible. So almost anything that we might want to say about the state of the world or about the effects of actions, we can express that in logical terms. Another nice thing about logic is that inference is very mechanical. So once we have some knowledge base that represents everything that we think is true about the world, and we have some rules of inference, then it's pretty straightforward to write a program that can apply those rules of inference to our knowledge base. So we turn the crank and we get new logical inferences out. And if we believe the facts in our knowledge base and we have confidence that our rules of inference are correct, we can be confident that those conclusions will be true. So that's the vision, that's the dream. We want to have a sort of artificially intelligent machine that knows things about the world and that we can ask questions and it can tell us things that logically follow from what it knows. There are some different logical formalisms that we might use. We're going to start with a simple one called propositional logic, and then a little bit later we'll talk about predicate logic, which is a little bit more expressive. So, and hopefully all of this will be fairly familiar to those of you who've taken a discrete math course. So we'll move through it a little bit quickly. We're talking about propositional logic or the propositional calculus. So the step one, I think, is to figure out what that means, what we're referring to. So looking at chapter 5 here, and let's start with the syntax of propositional calculus. So in propositional calculus, right, we're talking about propositions. So these are sentences or statements that have some truth value. They're either true or false. And these propositions can be atomic propositions or they can be compound propositions. So atomic propositions are represented as a single symbol, and we can think of this as a variable that can take on either the value of true or false. So there's a paragraph here talking about how we can interpret what these atoms mean, but I think for our purposes it's fine to just think of these as variables, to start with a lowercase, and they can be either true or false. So examples, AI is fun, lit L1, so this is referring back to his electricity example, live outside, sunny. These are all variables. They can take on the value true or false. So those are atomic propositions or atoms, and then once we have a set of atoms, we can build compound propositions by combining our atomic propositions or other compound propositions with our logical connectives. And hopefully these are familiar to you. So negation, conjunction, disjunction, etc. And notice that P or Q here are themselves potentially compound propositions. So we have here a nice sort of recursive definition of the syntax of the propositional calculus, right? Every proposition is either an atomic proposition or it's a compound proposition of these forms, and then so those can be compound propositions, etc. This also describes the precedence of these operators and the fact that you can use parentheses to disambiguate or to modify the precedence. So that's the syntax of propositional calculus. This describes which strings of characters represent valid propositions. This doesn't say anything about how we interpret them, what they mean. So then we have to think about the semantics of the propositional calculus. The semantics of the propositional calculus. So the first term we want to talk about is an interpretation. So if we have some set of atoms, our interpretation is just an assignment of true or false to all of those atoms. So this is described here as a function that maps every atom to either true or false. And that's just a description of the way the world is, under one possible way the world might be. So for an example, Here's an example. AI is fun is one atom, happy is an atom, and light on is an atom. And one interpretation involving those three atoms would be that AI is fun is true, happy is false, and light on is true. There are obviously other interpretations involving those atoms. In fact, there are 8. And here they are. We can enumerate them. So every interpretation is just an assignment of true and false to every possible variable. So if we have 3 atoms, we're going to have 8 possible interpretations. And if we're looking at this one here, AI is fun true. So that's one of these first 4. Happy is false. It's one of these 2. And light on is true. That gets us to this one. So here we're looking at this interpretation among all of the possible interpretations involving these atoms. We can talk about the truth of propositions within an interpretation. So that's what's happening here. He lists a bunch of propositions involving these 3 atoms, and he assigns them a truth value on the basis of this interpretation that we've chosen. And where are those truth values coming from? Well, I've added a couple of extra tables here, and these truth values are coming directly from our understanding of the semantics of these connectives, the truth tables that define what these connectives mean. So I've just filled in this additional column here shows the truth of not AI fun under every interpretation, and the truth of AI fun if happy under every interpretation. And remember, we're looking at this one here. So not AI fun, well, under this interpretation, AI fun is true, so that means not AI fun is false. AI fun if happy is true, because in this interpretation, happy is false, and AI fun is true. And when I plug into my truth tables here, that's the result that I get. So let's look at some additional terminology here. We can talk about a knowledge base. So a knowledge base is just some set of propositions that we've decided is true. It's our sort of starting point, and we'll call all of the elements in our knowledge base axioms. And a model of a set of propositions, or of a knowledge base, is an interpretation in which all of the propositions are true. So a model is an interpretation that's consistent with a knowledge base. And so then we can start talking about logical consequences or entailment. So if we have a knowledge base, then some proposition is a consequence of that knowledge base, or is entailed by that knowledge base, or logically follows from that knowledge base, if for every model of that knowledge base, that proposition G is true. So in any world in which the knowledge base is true, then the proposition G must be true as well. Probably the best thing to do is to work through an example of this. So let's say that our knowledge base includes the axioms that AI fun if happy, and it also includes the axiom happy. So the next thing we might do is look for interpretations that are models of this knowledge base, and let's try to find all of them. So we want to find first all of the interpretations in which this proposition is true, AI false if happy. So it looks like there are 4 of them right here. We'll grab those. And there are 2 more down here. So there are 6 possible ways the world could be, 6 possible assignments to these 3 variables that would allow this proposition to be true. Now let's consider our second proposition, our second axiom, happy. And let's look for all of the interpretations that model that axiom, happy. So it looks like there are a couple here. And a couple here. Now for an interpretation to model our knowledge base, it has to be true for every axiom, right? And it looks like there are only two, maybe I need a new color here. It looks like there are only two interpretations that satisfy that. These two, right? In these two interpretations, happy is true, and AI fun if happy is are true. And so now, maybe we want to know if this knowledge base entails AI is fun. Is that true? And we can see that it is, because we here have every interpretation that makes our knowledge base true, and in each of those interpretations, AI is fun is true. So if our knowledge base is true, then AI is fun must be true as well. And that's not surprising, right? Our whole knowledge base just says AI fun if happy and happy, so we would be surprised if AI fun didn't turn out to be entailed. Okay, so hopefully you recognize that this is an exciting moment, right? One thing we've accomplished here is we hopefully understand this idea of entailment. But entailment is kind of what we want, right? We want to have a machine, a super intelligent machine with a knowledge base, and then we want to be able to ask it about propositions and have it tell us if those propositions follow from that knowledge base, right? That would be handy. So to be a little bit clear, if we flip ahead a little bit, we'll see a different symbol, right? This symbol instead of this symbol. This entailment is just a statement that a proposition does follow from some knowledge base. This is a symbol that says that we can infer using some particular mechanism, some particular proof procedure, that a proposition follows from a knowledge base. So this is a statement about whether that's true. This is a statement about a particular way of doing it, whether we'll get there. And the exciting thing that just happened, maybe you weren't paying close enough attention to notice it, is that we now actually have an inference procedure. We have a proof method that will allow us to perfectly solve this problem of entailment. So maybe let's just quickly pop ahead to look at proofs, and there's some terminology here, right? A proof is a mechanically drivable demonstration that a proposition logically follows from a knowledge base. That's what we're interested in. A proof procedure is how we do that, an algorithm for driving these consequences, and here's that symbol I just introduced. It means that G can be proved or derived from the knowledge base. And what we want are proof procedures that are sound, meaning that we only derive theorems that are actually entailed by our knowledge base. We don't make mistakes. And we also want a proof procedure that's complete, meaning that if it's possible, if something is entailed, then our proof procedure will get there. And I just performed an algorithm in front of your very eyes that actually satisfies both of those requirements that we might want. The algorithm is just to fill out a giant truth table containing the every possible interpretation, right? Every possible truth assignment to our atoms. Plug in our knowledge of what our connectives mean to figure out which interpretations make our knowledge base true, and then check to see if in every one of those interpretations our the theorem that we're trying to prove or the conclusion that we're trying to reach is true. And we can actually do that, so I'll leave it as an exercise to the reader, but that can be done in 20 or 30 lines of Python. We can fill out such a truth table and we can run those checks. So that's pretty exciting. We have a sound and complete proof procedure for propositional logic. So if you present a knowledge base in propositional logic, I can write an algorithm that will derive everything that is derivable from that. So hopefully you've seen the bad news. The bad news is that these truth tables can get unmanageably large, right? And they are almost always unmanageably large. So every time I add one more atomic proposition, it doubles the size of my truth table. So this inference algorithm that I just sketched out requires exponential time in the number of atomic propositions. So that makes it not very useful in practice. So, that was good news. We have this sound and complete proof procedure, followed by bad news that this particular inference algorithm is not efficient enough to be useful. And some even worse news is that, in fact, there probably is no efficient algorithm for calculating entailment in propositional logic. So it's been shown that this problem is co-NP complete, which for our purposes just means it's probably as hard as NP complete, which for our purposes just means that it's hard. So that's discouraging too. So here, this essentially always takes exponential time, and it turns out that it's known that there's no algorithm that's guaranteed to take less than exponential time. So that's sad. What an emotional roller coaster. There's good news too. The good news is, just like for lots of NP-complete problems, there are plenty of inference problems that are hard, or there are at least some that are hard, but it turns out that lots of them are easy. The other good news is that if we are willing to restrict the set of propositions that we're going to allow into our knowledge base, if we're willing to put some restrictions on the form of the axioms in our knowledge base, then we can actually end up with provably efficient inference, actually linear in the number of entries in our knowledge base. So that's going to take us to our next topic.